Hello everyone, my name is Burhanuddin Lokhanwala, and today I will be presenting my data mining and analytics project, School Budget with Machine Learning. In any education institution, budget management is critical. It involves allocating resources efficiently across various departments and activities, ensuring that every penny is well spent. Traditionally, budgeting processes are manual, which leads to inefficiencies, especially in classifying budget categories. The goals of this project is to automate the classification of school budget line items using machine learning algorithms. Specifically, we use machine learning to predict categories for each line item uh, in the budget dataset, including both numerical features like total cost and textual features such as item descriptions. So this will ultimately reduce administrative burden and promoting transparencies in educational finance management. So let's start with the background on the dataset. School budgeting is a very complex category. So accurate classification of dataset and budget line items is crucial to ensure compliance, optimizing spending, and enhancing decision making. So the dataset we use contains records for 1,560 budget line items, each with 25 columns. The features include both numerical data like FTE full-time equivalent and total funding, as well as textual data like object description, which describes each budget line item. One of the main challenges was the presence of missing data, which is typical in the real-world datasets. I also had to handle the mix of structured, numeric, and unstructured text data, which adds complexity to the model. Before training the model, I had to pre-process the data by imputing missing values and encoding categorical data to ensure all features were suitable for machine learning algorithms. This graph showcases just that. Now let's go to data processing and exploration. For missing values in numerical columns, we use mean imputation, where missing values are replaced with the column's mean. For text features, empty strings were used to replace missing data. So this would preserve the structure of the text columns. So I extracted the features from the text columns using count vectorizer, which converted the text data to the numerical data. This has the n-grams, which are the sequence of the adjacent words. This allowed the model to capture the concept of patterns and single words as well. And numeric features like max app scaler, which normalizes the data, ensuring that each feature it contributes equally to the model, especially important models like logistic regression. So this was the coding aspect. This is the data processing, which handled the missing values which were present in the numerical features FT. Then the data exploration for the categorical features, um, and then the key code for the the count vectorizer and the vectorization. Here, the correlation matrix shows that there is very little to no correlation between FT and total. And the, now let's talk a little bit about the machine learning methods I have used. So, logistic regression was chosen as the baseline model due to its simplicity and interpretability. It's well suited for classification tasks, especially when the relationships between the features are expected to be in a linear pattern. Then, uh, then comes the pipeline design. The model's design follows a pipeline architect that integrates all necessary steps: data processing, extraction, model training, and evaluation. So, we automate the preprocessing of the model, handle the numerical and category and textual data. We have the pipeline creation, then the classifier, which is the logistic regression was within the one versus rest classifier, which we'll talk more more further on. And then this model basically makes it very modular, reusable, and it simplifies experimentation and scaling since it's a step by step and a very linear procedure. Now, let's discuss the different stages of the pipeline. The pipeline begins by selecting the numeric and text data separately. Numeric data goes through imputation and scaling, while the text data is processed to the count vectorizer. These transformed features are then combined using a feature union. For classification, I use the one versus rest with the logistic regression with random forest, which which helped me to handle multi-class classification very efficiently. This is a diagram which shows the model accuracy progression across the different steps. So we go from the original data, the logistic regression, and then the logistic regression imputed, the text data only, all of the data, the feature union, the random forest, and then the random forest with the custom estimators. As you can see that the accuracy is seen the most when the whole data set is used. Over here, as you can see the same. When we go across the different configurations, again, this is a bar chart representation of the accuracy. Now, let's come to the model evaluation procedure. We use two evaluation metrics for the model. So first, we use accuracy. Accuracy measures how many predictions the model got right overall. It's a simple intuitive metric, but it doesn't always give the full picture, especially in cases of imbalanced data. Now, with log loss. Log loss evaluates the model's uncertainty in its predictions. A lower log loss indicates that the model is confident in its predictions, making it a more informative metric. So over here, when we look at the accuracy and the log loss, we can see our logistic we can see our regression, the present results. The logistic regression model achieved an accuracy of 92.8%. However, the log loss was of 1.845, indicating that while the model performs well, there is room for improvement, particularly in improving the model's confidence. Now, while high accuracy is desirable, a model that has low log loss is typically because it indicates that the model is confident in its predictions even when they are wrong. This suggests that there's further fine-tuning that is required, that is necessary to balance accuracy and confidence. As we can see over here, we can see that there's a very significant difference between the accuracy and the log loss. There is more room for improvement within the model. Now, let's get to the visualizations for the predicted probabilities. Let's go to the heat map. So the first visualization over here is a heat map of the predicted probabilities. This shows us the model's confidence in predicting each category. We can clearly see when the model is more confident and when the model is uncertain using this graph. Now, the second visualization is the category distribution visualization, which displays how often different categories were predicted, offering insight into the model's strength and areas where further tuning could be beneficial. So now finally, it's time we discuss the results. So the model was performed well overall, but we noticed that the position type and the function features were the most important in making predictions. These features had high importance scores which aligns with our expectations. Textual features, such as object description, contributed highly to improving the model's performance, especially when the budget descriptions provided additional context. So, although the accuracy was high, the log loss revealed that there is room for refinement. The model could be further optimized for better certainty in its prediction. Now, let's get the concluding remarks and key findings. To conclude, this project successfully demonstrates the use of machine learning to automate the classification of school budget line items, achieving an accuracy of 92.8%. This emphasizes the strengths and the weaknesses. The combination of numeric and text data proved to be the most effective, although improvements in model calibration are needed to reduce log loss. Now, what are our limitations? Random forests performed well in certain cases, but showed lower accuracy on the budget data, which may need further feature engineering or more specialized tuning. Now, our key takeaways. We saw model performance. We have a high accuracy of 92.8%. We have a log loss of 1.845, which is on a lower end. Textures data significance. We have an integration of textual data which significantly improved the model's classification ability. And we use feature engineering and advanced technologies to enhance processing and machine learning tasks. Now, the practical impact of this project. The project provides scalable solutions for automating school budget classifications. This will reduce administrative workload, enhance financial transparency in education institutions. Using machine learning can solve can solve these problems and can better allocate resources, ensuring compliance, and make the data-driven financial decisions. Now, our future work and recommendations. The future work could focus on refining text features extraction by exploring more advanced techniques like word-to-vector or BERT, which may capture deeper meaning in the text. And mentioning about the model alternatives, we could also explore more advanced ensemble methods like XGBoost to to improve performance on complex data sets. Real-time deployment, real-time employment, like integrating the model in the real-time budget systems, could help the schools make faster, data-driven financial decisions. That's all for me, folks. Bye bye.